want to sort of reinforce some things about the course and what we've done this semester and what you can do with it going on in the future. And then I'll save some time at the end for any questions about whatever. Okay? About paper, about final, about why is the sky blue, whatever you come up with. All right, so first things first. What have we done this semester? Well, if anything, we've reinforced and reinvigorated and brought back some long dormant math skills that you had. And of course, what were those math skills that you had? Addition, subtraction, multiplication, and division. And maybe we picked up a new one. Maybe you learned a couple of other things, like, well, we started with PEMDAS. Hopefully that's rattling around in some of your brains. Maybe somebody learned that if you turn your phone sideways, you get more buttons when you're using the calculator. That'd be a good skill to have. Okay. Maybe, just maybe, some of you have learned how to use a calculator, which when I met with somebody today, I found that they were still using their calculator wrong. And for me, maybe I should have spent some more time on this, but since it's the last day and it's my last shot, I'm going to teach you one thing you should be doing when you're using your calculators. We're using parentheses. So if you have something like in the homework where it is you're doing your choosing and you've got 0.6, 0.4, this is raised to the third power, that's raised to the third power. I think this is 6 times 4. This was 20. Right. Some of you will put 20 in, and then you'll do 6 to the third, and then you do 4 to the third. Or if you have a nice calculator, you can just write the whole thing using the little caret button. So you would type 0.6 to the caret 3. Man, that would have been great. So some of the mistakes that you made weren't math mistakes at all. They were just not knowing how to use a calculator. And I'm going to add that to the class the next time I teach it in person. We're actually going to talk about how to use a calculator the right way. So you've got math skills, except for when you forget them, right? You take them for granted. You get maybe a little sloppy in your homeworks. That's another thing I'm not going to allow the next time I teach this class. God-awful sloppy homeworks between people who can't draw an 8 or write in the English language, or at least anything that appears to me as the English language. You gonna work on that? Thank you. All right. Or perhaps just reinforcing what a sentence is and how to write a sentence. That would be a good skill. I've learned a lesson. Okay. But you brought most of these coming in. Again, addition, subtraction, multiplication, and division. I will give you the exponent thing was hard. You had to add that skill. But other than that, everything we've done mathematically was not that complicated. I did not force you to learn calculus. Can we agree on that? What took a little while is understanding what it is that we're doing by talking about numbers. And for us, numbers are data. And if you're going to do anything with data, you have to understand where it comes from. So when we started the class, we talked about things like how to measure. ordinal variables, continuous variables, count variables, time variables, nominal variables, which are just categories or names, and then finally our good old friend, the dummy variable. A lot of thought goes into when we observe a phenomenon, how are we going to measure it? How many different categories could we select? Is there a better way to measure what we're observing? So let's take something like a presidential election. What are some different ways we can measure the outcome of a presidential election? Okay, so you have a popular vote. You have the Electoral College vote. How do you measure either of those? Like, tell me a number. Okay, so you could say something like 309 and whatever the other number is. Okay, what are other ways to represent this information? Not there yet. Just this information about who won and how we can tell that somebody won. So you told me that there's this thing called the popular vote. We can actually count the literal number of votes. 62.5 million for Hillary and 60 million for Trump. We could graph it. What's another way to represent Hillary's vote total? Yeah, we could do it as a percentage. So you're telling me that 48.1 means the exact same thing as 62, 543, 672. Right? You are. Yeah, they do mean the same thing. We're measuring the same concept in a different way. We have a raw vote total, and we also have a percentage or a proportion. And we can do it that way. You can do the same thing for the Electoral College. Okay. There's one more interesting way in which to measure the outcome of the presidential election. How would that be? Very simple, easiest way of measuring. Yeah. Final score. Right? That's a simple way. You could measure it as a dummy variable. You could measure the person. You could measure the political party. Republicans won. Okay. So we have a dummy variable. We have an ordinal variable if you wanted to rank order them. 1 through, in South Carolina had 7 people. I got a write-in vote. I'd like to thank the one person in the world that gave me a write-in vote. Okay. We could try to do it in a more continuous fashion by having really, really large numbers and focusing on the sort of actual count of the vote, or we could do it in terms of a proportion. Okay. This matters. Okay. This matters because how we decide to measure what we're observing can give us a contradictory result. So if I measure the presidential election by popular vote, how is that different than measuring the presidential election by a dummy vote? How so? Yeah, so again, how we measure the outcome of the presidential election can give us different results. If we measure it in terms of the popular vote, which Clinton won by 2.5, 2.6 million votes, so more people wanted her to be president, that will give us a different perceived outcome than a dummy variable effect, or even worse, by looking at it in terms of the proportion of electoral college votes. Right? There's a really big gap. Right? It appears that if you looked at the electoral college, Donald Trump won more than 300 electoral college votes. That's like 63% of the votes. If you were to look at it and go, oh, well, he got 63% of the electoral college vote. Yeah, but he only got 46% of the actual real vote. But that doesn't matter, right? Because which one is the one that actually picks the presidency? This one. Right? Okay. So how we measure is important. You actually have to put some thought into, I want to capture this concept. I need to be careful in what it is that I'm measuring, and also what are the alternatives to how we measure it. Once we have data, and the data sets that I deal with are thousands of observations. You look at something like the National Election Study or the General Social Survey. Thousands of observations. You need to figure out a way to summarize that data. And the two things that we looked at in this class were measures of central tendency and measures of variation. Our measures of central tendency are sort of like our expected value or our expected outcome. So we can take data and say, what's the most likely outcome? That could be the mean, it could be the median, it could be the mode, depending upon the shape of our data and how we chose to measure it. Variation is how different is our data? What is the spread that we observe? Do we see a lot of variation in the data, or do we see a little bit of variation in the data? Understanding what our data looks like will help us understand what we should do with it and how we should analyze it and how we should even think about perhaps what we're observing. So we spent a little time on this. And this was good, because this helped you sort of start doing actual math. And you had equations. And I could start putting letters in where numbers should be. Okay. So a very simple statistic to calculate the average or the mean of something. We got to learn that this sigma kind of looks like sigma chi. Sigma chi over nu. The sum of x divided by n, that's our average. Now, the reason that we make the transition from calling it an average to, in a statistical class, a mean, is because we need you to understand that there are more intricate ways to explain what it is that you're doing. So if I'm teaching my daughter Abigail the mean, am I going to say, well, Abby, x bar equals sigma x divided by n? Why wouldn't I do that? Yeah, she doesn't know what sigma is. She doesn't know what x bar is. But when you're learning, we would tell you that the average is the sum of all your numbers divided by the number of numbers that you have. And that works. Because that is, well, that's easy. That's more intuitive. Right? Add up all the numbers I have, divided by the number of numbers. And that's the average. But when we're doing statistics, that's too simple. Because it's not written in the right language. Mathematics has its own language. An object like x bar, the sum of x, or the average mean of x, is a function. And if you continue on with statistics, you'll start to think more in terms of this representation here is not an equation, it's more of a function. It's how you compute what you're looking for. So this is your first statistic. This is usually the first one that we teach you in elementary education, and it's the first one we do in an intro statistics class. It's the one that's most familiar to us, but this is your first statistic. And you'll notice that once you learn this, then the next step is doing your standard deviation. And your standard deviation is, I'm going to write it wrong, so I better find it the right way. I know it's the sum of x bar minus x over n, right? Isn't that our standard deviation? Where we're trying to find the average difference from the mean. Oh, why didn't you write that down? You're going to whiff on something that looks so simple. It's about right. And all it is an extension of the mean. So once we have this, so once I was able to teach you measures of central tendency and variation, oh, that's a kick-ass one too. You gotta admit, that's a pretty good one. Oh, you suck! You oh! You saw it though. It was there. Fuck. Okay, but not great. That last one was beautiful. I was going to save that one. That was such a good one. All right, this is not too bad. I need a drink. That was beautiful. That was such a good one. All right. So now that we have, we've planted a seed in your head. You are now thinking about data being represented by numbers, right? So this data set of 1,000, or whether it's 19 numbers representing a feeling thermometer towards Hillary Clinton, right? You all went up, you typed in your number, and then we summarized it in terms of a mean. It allows me to do two things. One, I get to draw a normal curve. And the normal curve is important because, well, you're going to use it all semester long. What do I do with my pen? And as long as you understand that there is out there your mean, right, our mean score, and that those scores have a distribution, we can then find you as individuals in that distribution. So, somebody here wants to take the LSAT, the law school admissions test. We know that the people who take the LSAT have to score between 120 and 180. I also know that the average LSAT score is about a 150, I think it's 1. Well, now you can place yourself in the range of scores if you have two pieces of information. One, the average, which you have, the mean there, and two, the standard deviation. Because the standard deviation is going to tell us how skinny or wide, or what other euphemisms we can have for girth of the distribution is going to be there. So it's either going to be little variation, so a small standard deviation, or we're going to have a bigger standard deviation. And that's going to spread our numbers out or make them more compact. And so we then moved into z-scores and finding out how, no matter what our mean and standard deviation is, those two numbers will give us a z-score that is uniform across all applications. Even when we change it from our score among the set or the mean of what we have, our sample mean, relative to the population mean, or our difference of two groups versus the expected difference between those two groups. So we spent a lot of time talking about finding our observation within the sample, finding the sample mean within the population mean, finding the difference of whether it's means or difference of proportions between two groups relative to what we would expect to find in the difference. So the goal in teaching you this z-score thing is to, one, start to get you to think about the differences between samples and populations. So that's one benefit. And then two, sliding into probability theory. And then hypothesis testing. So the trick is, once you understand that the space under the curve the area under the curve can also be used to represent probability. because they both equal 1. Well, that's when now we can start making claims from our data. We're going to use probability theory to start making claims. Whether it's you all are different than the responses in 2008 towards Hillary Clinton's feeling thermometer, right? Wasn't the average in here something like 38 or something? Like, you guys really didn't like Hillary. And the average score was in the 60s in 2008. I said, oh, you guys are awful people. You're so different. You're outside of our 95% confidence interval. You guys are really weird. That was a claim, right? I was saying something about you as people. How did I do that? Well, I had to relate you, my sample, to what I thought, and at the time was assuming, for math fun, was the population. When really it was, what's the probability that I get this sample out of another sample of a larger population? But, you know, you got to make some stuff up sometimes when you teach. Just a little bit. So now that the area under the curve, I'm going to try this again. Pretty good. You're not feeling it, Aaron? You're like, no, that one kind of sucks. I think it's kind of good. I understand this tail here's a little. By translating area to probability, we can start now. Why? Why do you do this? I think what you guys should get me for Christmas is a new tablet. Can you work on that? I can't put that on a recording. Yeah. Do all of you have to get A's? Like, really, all of you? Because then it's really apparent. Like, can a few of you sacrifice and be like, Ben's screwed. Don't tell him. Ben and Christopher are screwed. All right. So we get probability. I get probability theory. We can then talk about area as probability. And as long as we come up with a set of rules and how we interpret that area, which is now probability, we can do hypothesis testing. So when we introduce hypothesis testing, I got to give you a framework. I have to explain to you, all right, we're going to use that area under the curve, which is now probability. It's now the probability that your sample creates a difference or a relationship. What's the probability that we see that in your sample if it's drawn from a population? So we're just going to come up with some rules about how this is going to work. So the first rule in doing hypothesis testing is that you have to state your hypothesis. But that's easy, because one of them we give you automatically. We give you the starting point. The starting point is always the null hypothesis. And the null hypothesis is always the same. There is no relationship between blank and blank. There is no relationship between gender and feeling thermometer scores for Hillary Clinton. No relationship between blank and blank. That's always your null hypothesis. Grading the chi-square homeworks, there's no relationship between the direction your front door faces and your likelihood of being burglarized. That's the null hypothesis. So whatever it is, there's no relationship. None. We shouldn't see any difference. Then the tricky part is when you're constructing your alternative hypothesis to just say that there is a relationship. That's all you have to do. Now we can be more narrowly focused, right? We can have directional hypotheses. We can say that being a woman makes you more likely to like Hillary Clinton. We can say that being a woman makes you less likely to like Hillary Clinton. Or we can just say that there's a difference between men and women in general. So you have choices with your alternative hypothesis, but for the most part, you're exerting that there is a relationship. We should see a difference, whether it's a difference in means, whether it's a score that's far away from what our suspected population mean is. The nice thing about the null hypothesis, again, every research design should have one. Your decisions about which one are true, sorry, I shouldn't have said that word. Whew, that was a bad word. Not true, not true, not true. Which one you will accept or reject, the null hypothesis as the default, well, that's the bulk of our outcomes. So you're going to have really, really good data, really, really good evidence that it's clear that there is a relationship. Okay. Now, once I've taught you that, then we talk about this thing called the decision rule, and we have a standard in the social sciences. The decision rule is always 0.05 or 95% confidence. That leaves you with 5% to play with, depending upon what your alternative hypotheses are. And because we spent so much time, so much time, back in October, going over Z-scores, that after the hurricane, I'm like, literally, the only thing these guys are going to learn is Z-scores. That's it. That's all they're going to learn. Because we spent so much time on it. You now have the framework to say, all right, I understand hypothesis testing. All I need to do is set, again, putting this as bucket on the floor, draw my curve. I expect, if I'm not going to reject the null hypothesis, that I have to be in that middle 95%. And some of you even learned the magic number. 1.96, magic number. If my z or my t is greater than 2 or less than negative 2, I'm good. Right around 2 is that magic number. Because that'll be great. Then I'll be able to reject my null hypothesis and say, yeah, there's a relationship. It appears as if gender matters when evaluating Hillary Clinton. And then this is where I leave you. Right? This is where you're set up and you're ready to go to keep going on. one of the last things I introduce is the fact that there are other distributions out there than the normal distribution. The first one is the chi-square distribution. And this one's slightly different because it starts at 0 and then it just keeps on going. You calculate chi-square, you put it on a line, and you ask yourself, am I in the do not reject or the reject area? Same concept as the normal distribution, but just a different shape. And now that you have that, you can do the Poisson and all sorts of distributions. Because no matter what you come up with and what you interact with, when you see something that looks like a test statistic, like a t or a z or a chi-square or a beta or whatever it is, in your mind you're thinking, all right, what's the probability level? Am I in that reject area or am I in that do not reject area? If the probability that is reported, if probability is less than you can reject the null hypothesis. In some cases, it'll be a difference of means test or a difference of proportions. It might be a chi-squared. It might be, if you keep going, a beta coefficient. Is this beta different than 0? And that's when you look at the output and you go, all right, where's the probability of it? Right? Where's the score for that coefficient? The next step, and I you know, assuming you all pass this class, which you all can, what you should do is you should keep going forward, right? Because for this to mean something, you're going to have to do multivariate modeling. Because what we need to do in a statistical method is we need to consider that there are multiple explanations. This is something that political science does a lot better than the other sciences. Over the summer, there was there's a book out, and there was some articles generated about a phenomenon known as p-hacking. The medical people are the worst at this. So things like the New England Journal of Medicine and all of these studies that come out and tell you that chocolate's good for you, dark chocolate's bad for you, you should drink wine every day, like those sorts of studies. The problem with the medical field is that they can start out with a big model like this, where they have lots of explanations. So whether or not I have a heart attack in the next year, one variable might be the amount of wine that I drink, right? What could my other variables be about whether I'm going to have a heart attack or not? Yeah, my weight, my diet, my astonishing lack of exercise. Actually, exercise is bad for you. It gives you heart attacks. If you're out of shape, that is. I think they should put an emergency phone on the second floor So that way when I go up the second floor, that's where I'm going to have my heart attack, and I can pick up the emergency phone. And the other stairwell over here on the side, it's on the third floor. Man, I'm not going to make it to the third floor. I'm going to have my heart attack on the second floor. That's where I need it, in the stairwell. But this is what the medical people do. They run the big model, and they go, that's not significant. That's not significant. That's not significant. And what do they end up with? They end up with a variable that has like one, well, a model that has like one variable in it. And which variable is it? It's the chocolate variable. There's a story out this week. And I know you all love talking about sex with me, because if you haven't been scared enough by the penis size examples. There's a story out this week from Britain that says that landscaping your pubic region increases the likelihood of you getting an STD. You want me to explain it to you, Nick? We should go outside for a second. And I saw that story, and after I clicked on it, and I'm like, oh, this is going to be another p-hacking one. Because these doctors, they might understand why I had my heart attack, like my heart is no longer beating, but they don't know anything about social science and explaining human behavior that led up to my heart attack. They found a really high correlation between people who had removed all of their pubic hair and the incidence of STDs. And therefore, in their special little brains, that means that there must be a cause. There's something about people who don't have pubic hair that leads them to have STDs. Now, we're social scientists. What do you think, just out of curiosity, might be the number one predictor of whether or not you have a sexually transmitted infection? How about having sex? And the frequency in which you have sex with multiple people. Do you think that was in the story at all? No. This is really bad in medical journals. And that's where all of these ridiculous stories come from about wine and chocolate and the number of people you have sex with, and all the... I'm going to start doing research into that, because apparently that's the easiest way to get published. Because what they are doing is they're focusing on the p-values for these betas, and they're of the mind if it's not significant, you should take it out of your model. But there's this thing called correlation, which allows the betas themselves to be correlated, and therefore it hides the effect. Yeah, and I want them to be different. I don't want them all to be related. Yep, you'd be p-hacking. And that's what they do. And all the statistics people know that they do it, but the New York Times doesn't understand it when they publish about, the latest medical journal. Nope. Yeah, right. Wine's great. If one glass of wine is great, I should drink 5. If one glass is good for my heart, imagine how much a bottle would be. All right? And it's not the wine. It's the fact that when you have a glass of wine, what happens to your body? You relax. So it doesn't have to be wine. It could be a beer. So that's what you've learned this semester.